Cool. Okay. Let's define connectedness. We're actually going to do it through a separation. So let X be a topological space. And a separation of X is a pair. And then we call them U and V typically, of disjoint and non-empty open subsets of the topological space X such that their union is the topological space. And then we're going to say that the space X is said to be connected. The big idea. If there does not exist a separation, basically. And so connectedness is given a negative definition, which means proof by contradiction all over the place. And there's an alternate definition we can give that's useful for proving stuff later. It's a space X is connected if and only if the only subsets of X that are both open and closed are both open and closed.
Please go ahead.
Yeah.
I think I need to process this at a slower pace. So I just need to figure out first. I'm trying to figure out the disjoint, non-empty, open subsets. Trying to understand, figure that out. I don't know.
I'm going to put this definition up, and then I'll give you.
Okay.
Yeah. Let's see, both open and closed in X, and then R. The empty set, which is given by that symbol, and the space itself. Okay, yeah, so for notation, for terms, so disjoint. So what it means for U and V to be disjoint basically means they don't intersect. So if I take the intersection of the elements in U and V, then there should be nothing in between them, right? So disjoint this idea they're separated. So if I intersect them, there shouldn't be anything in their intersection. So this set right here is not disjoint from this set. Because if I had some A and this is B, the issue is if I take the intersection, that exists. So that actually has elements, it's not empty. Disjoint is saying, okay, well, on the other hand, what if I need a U and a V, so that if I do try to take the intersection, it's just empty. That's disjoint. And then, what was the other thing? Non-empty is basically not equal to
open means basically no boundary, or
well, and on the real line, yeah. So it would be open. So some subset U is open in X. Basically, if this is in the topology of X. So U in, actually I'll do this. So U is in the topology of X, where T is the topology.
So just draw the real number line. And let's say we wanted to split that into two. Could we do it by having both sides open? So like draw a line in the middle. Okay, split that split it into two parts, right? So that's U and V. We created a separation, or can we? Well, is it possible for U and V to both be open and still cover the entire real line? Right, because if I make U open,
which would be like a ray starting from here. So if this was some R, this
right,
is from here, then U and V, if we're trying to make some sort of a separation, we'd have to have U as 2R. And V would be R up to there. The issue is if we look at the definition, they may be disjoint, right?
so that is short, yeah.
They are disjoint because if you try to take their intersection, they actually don't have any elements in common. The only issue is this needs to be satisfied. That they have to be disjoint and their union needs to be the same. So the real question we have to ask then is the union of minus infinity R, if I take this union, is this equal to the space? And we're missing the whole. We're missing R.
R itself.
And so that's not true. So it fails to be a separation.
So what we could do is we could close the left of V so that the union would be all of R, but then what did we just do to V?
Make the partially closed.
Make it
Exactly.
closed. So a separation is, we want to have the whole space covered by the union, and they have to be open.
So what that's saying is that there's no way you can jiggle around so that I can have. Go until R, but then consider it, and then go until like R, but then you can sort of shuffle it.
Right.
That's not possible. That's
So I mean, intuitively, connectedness is kind of nice. It's basically saying it's connected. You can't, it's not multiple parts. If it's connected, it's just gonna be all connected. It's not, you can't find a way to break it into smaller subsets of itself that don't have any relationship to each other.
Separate.
So that's the gap between what we think is intuitive visually versus the language that has to be developed to do it rigorously can be frustrating. And but the topologist needed something to do, I guess. Move to specifically to real line, so connected subspaces on R.
One second, continue over that.
Okay. So here's the overarching goal here. And I recognize that now I'm thinking there's a bunch of definitions from last semester that you can Google, because Wikipedia is really good, and then they have all the definitions. So if you want to tie everything together, prove that the real line is connected. So like what we just showed earlier is it's impossible to basically split, but we just chose a single example, and that doesn't constitute a proof. So we'll prove it, and also, so are the intervals and rays. You know what rays are from like set theory or algebra?
That's you
So-
like start a number, then it's forever.
Yeah, so you start at an open, closed or open point, and then it goes off and. Yeah.
Do that.
Because like, so what we had in that previous example, those were rays, because you're starting at some open point in this case and then going off to whatever. And those were connected, so because they're subspaces of R, but we have to prove it, so we're gonna come up with a definition. This is going to be a simply ordered set L.
So to be clear, the intervals, and I guess the rays can be either open or closed, and it's always true, it's still all connected.
Yeah, so intervals and rays will be connected as subspaces of R. So contained in the topology of R, they will be.
Right, but like the point is like they can be either open or closed, right? Okay.
Having more than one element is called a linear continuum. Basically, and we have three conditions. or sorry, no, this is those two conditions. So we need L to have the least upper bound. And that if we have two element, so if X is a semi in the ordered set, then there has to exist an element that is between your two elements. So the whole more than one element thing becomes out of necessity from this condition, because if you don't have more than one element, you can't have this property. Okay, so here's the theorem that we're going to spend a decent amount of time on, because it's basically going to get us to our goal. And once we prove this, then we can just take any interval, any ring, like, yay, and now it's connected, and then just not worry about anything else like that. So if L is a linear continuum, not shown here is demonstrating that R fulfills these properties, because that's from analysis if you really wanted to do that. In the order topology, then L is connected. And so basically we're claiming that there does not exist a way to take open sets of L that are disjoint from each other and also non-empty. That will get you back to L. And so are intervals and rays in L. Okay. So this is where the proof is a little kind of long, so I'll just keep wrapping it over and over and over again. So I'll start that here. Because we'll have to split it into some cases to get the contradiction all the way proven. So I'm going to recall, because it's been a little bit, a subspace Y of L is convex if and only if, basically, if we take all the pairs of A less than B in our subspace, then the entire interval, from A to B is closed of points of L. This needs to lie in the subspace Y. And the whole crux of the proof is we're going to show that Y, which is a convex subspace, of the linear continuum, is going to imply that Y is connected. Okay, so then we're going to define a separation and then do a proof by contradiction. Because the crux of basically every single proof for connectedness is you say, okay, we want to prove that something is connected. So let's just say it's not connected. And then that's going to lead to a logical, or it's going to contradict a definition or some sort of hypothesis later down the line.
We have one question. So explain how the real numbers have the least upper bound property. What is that?
Well, that requires me remembering what the least upper bound property is. I'm pretty sure, if I remember correctly, this basically, if you take subsets of R, then you're guaranteed the existence of the supremum for
The largest number possible.
what I forget is, because I've been thinking about closure, because closure basically you include all limit points, which corresponds to the supremum and R, or the infimum. But least upper bound, there basically is going to exist an element. So if you take the set of all elements that are greater than, okay, so if I have like, if we're in R. And say I choose the element 7. And then what we do is we define a whole set of the upper bounds, basically. So anything that is greater than in this order, based off of this operation less than, I would define on R. So things that could be in this set would include, like 8 or 100 or, 120. So it doesn't matter. Any number that is greater than 7 counts as an upper bound. But this says that this set has to have a minimum. And in all scenarios in which you choose an element of R, then there's guaranteed to be a minimum element if you take the set of all of the upper bounds. So the reason why it's interesting is because we use limit points for this, because if you really think about it, if I try to get really, really close, well, maybe 7.001, right? Well, that's greater than 7, but we could just keep adding zeros. So what about 7.00001? Well, now that's less than this, so that means it's a smaller upper bound than this is, 7. And so the zeros go on forever, but we're essentially guaranteeing that for any given x, that there's going to exist, x in R, there's going to exist a minimum element out of the set of, I'll just call it A is an upper bound, or A greater than x. Does that clarify this property?
So basically there's one number such that all the other numbers in the set are smaller than.
I mean, that's the thing, is that you can choose to think about it from all sorts of perspectives. I like the optimization perspective, where you're minimizing a set. But it depends on the practice, because if you're doing analysis, so if you're doing Calc 4, then what you would do is you'd use this to motivate limit points. And then take limits as you approach the ends of open intervals to close them. Topology says, oh, that's cool. So then use the definition of limit point and essentially give a name to points that you can add to something we call closure, which is going to be the set together with all of its limit points. But the thing is, there's always multiple definitions for everything. So it depends on your context and depends on the perspective you're coming from. But that's a good way to think about this case. Let's set up the contradiction here. So here's the contradiction. We're going to suppose exactly the opposite of what the theorem, of the end goal is. So we're going to suppose that y is not connected. We want y to be connected, so we're going to suppose that it's not. And the way we do that definitionally is we're going to assume that there's a way to separate it. So A and B are going to, that we're claiming that this is going to separate y. And of course, A and B are not allowed to be empty if it's a true separation. And they also have to be open in Y. So what we're going to do is we're going to choose the point. So we're guaranteeing that they're not empty. So we can say that there has to be an element in A, there has to be an element in B. And then for convenience, because it really doesn't matter what we choose abstractly. So for convenience, we're going to suppose that A will be less than B. Because it doesn't matter which way it goes, we just have to fix one of them because they're arbitrary elements. So that's going to tell us that the interval from A to B, because A is less than B, this is now a subset of Y. And in that case, the closed interval from A to B can then be described as some union of A naught and B naught, where A naught is intersecting the part of the separation A with the interval. And we'll define B naught in a similar way, where we intersect the other side of the separation with the interval. And then we take those intersection pieces, and together that will just put together the interval. And A naught and B naught, put a comma, A naught and B naught then are open in the closed interval AB in the subspace topology. Topology, which is the same as the order topology, same as the order topology, and our choice of A naught and B naught essentially guarantees that they're not going to be empty. The reason for that is because we have A in A naught. So we chose A with the bottom endpoint to be in this alleged separation. And so even if we intersect it with we're guaranteed to at least at a minimum have A. If you intersect a set that contains A with a set that contains A is in common with both sets. Therefore, it has to be in this smaller A naught. And then the same exact reasoning is we still have B in B naught, making A naught, B naught open and non-empty. So we're going to move forward with the separation. By definition, that allows us to say that A naught and B naught, which is this more specific intersection with the interval, they constitute a separation. Separation of what? Well, together their union that we chose over here gives the closed interval. So it's separating this interval, AB. AB. Now what we're going to do is we're going to just give a name to the supremum of A naught. And it actually doesn't matter. We could do infimum of B naught, but since we're using the least upper bound, we'll do this way. So C will be defined to be, in a notational note, is I got this from doing too much algebra, but I'll use triple indication that you're defining something. So I'm not saying that C is equal to, well, I can and I am, but it's more that I am choosing this by definition for the proof to be the supremum of A naught. Now again, if you think about an interval, and I'll draw pictures for this in a second, is that you got a closed interval on a real line. A is the bottom over here, B's over here. If we're assuming we can even separate that, that means the piece over here has to have the bottom, which has A. Piece up here is the top, has B. And then now we're saying, okay, so C is going to basically tell us kind of where in the middle this is going to happen. Because if the supremum, which is this, the least upper bound on A naught, it's kind of that upper boundary basically of if we're going to separate, it'll be at the top of that. And then consequently, it'll be the bottom of this part of the separation, which is above. Okay. So effectively, all we got to do is we got to show that C belongs neither to A naught nor B naught. Why is that a problem necessarily? Well, C is the supremum. And because L is a linear continuum, we're guaranteeing that C is it has to be an AB. Okay, so the fact that C is the supremum of this subset, which is intersecting a closed interval, C has to be somewhere in between A less than C less than B. And so if it's in neither of these pieces, then the separation is logically impossible. So then it has to be connected. So this has to be done in three separate, or actually we can do this in two cases. And I'll draw the pictures before I put all the garbage down because it'll look a little bit odd. So here's the visual, the intuition to motivate how this is going to work. So here's kind of a case, a subcase. If I take my closed interval A to B, right? Now I'm assuming that I've separated this into these open sets. And that means there's going to be, I'm going to claim that the supremum corresponds with the highest possible point. Okay. Well, that's going to present an issue because here is going to be that supremum of A naught. You could make the argument that would make B naught empty, which contradicts our hypothesis. The other way you could do it is that since B naught is open, then that means there's actually going to be some sort of an open element here. Because it's open, there's going to be a some point D. But we just said that C is the least upper bound to this side of A. So A is kind of this stuff over here. So it's A naught, and this over here is here's B naught. But now we're saying D is actually less than C. We just defined C to be the least upper bound on this bottom. So we cut it up like this, and now by definition, though, we're required to have a point that's less than C. Logical contradiction, so then this fails. And then the other case that we could have is here's A, here's B. What if we don't? So maybe C is not B, but it's somewhere less than B. So C would be less than B. So say we just choose somewhere less than B, doesn't really matter. Because the idea is now you can have this interval, this subset, that's guaranteed to be existing inside of A naught, and then here's B naught. And again, there's going to be another element. So it's the same problem presented here. So here's kind of where the B ends, so that this is top. This is no longer actually a least upper bound on D, because, or sorry, on A naught, because D is less than C. So this is the intuition visually what's going to happen. The symbols are probably going to look a little funnier, but just trust me that this is what's happening. So we're talking about this, both cases rigorously. And I'll erase and then D, well, I define basically it's given when we write it all out.
Okay.
But essentially it's a point in the interval that's less than C that's guaranteed to exist by definition of the way that the hypothesis is set up. Yeah. Okay, so here's the case one, which is basically just this stuff. So let me move. We're going to suppose, okay, so supposing that C is in B naught. This is the way we're talking about when I said let's choose to put C somewhere in that part of the separation. Then by hypothesis, it's impossible for that to be A. Because if A and if they're supposed to be separated, then these guys should not be in the same set, which means it shouldn't even be possible for this, if it's in here, to be in A. So either B is C or B is less than C. So two cases. In either case, it doesn't really matter. It follows from that in the hypothesis that, well, actually, it's not technically a hypothesis. We just showed it earlier. B naught is open in A specifically, that there is going to exist some interval of the form the C, which is a subset of this part of the separation. So this is guaranteed to exist in both cases. Now, let's turn to first case. C is B. we have contradiction immediately. As I pointed out visually, there's so many different ways you could see it immediately. And it's very rare that we accept something kind of like that, but we literally said it's on this side. It's supposed to be the supremum of it. And, you know, it defies how we define the contradiction in the first, or the separation in the first place. But to do the class separation for D is a smaller upper bound on A naught than C. Recall, C was defined, he's supposed to fulfill the role of the least upper bound. And then we just found another element that's guaranteed to exist that's less than. Okay, and then now we need to do the other case, right? So if C is then less than B, we note that this interval C to B does not intersect. Does not intersect the other piece of the separation, because we're still assuming it's separated, because C is defined to be the supremum of A naught. And then the interval that we're guaranteed to have D to B, which can be found as the union of simply taking C or D to C. And then moving up from C, oops, this is open. C up to B. This also does not intersect A naught. And again, as in both cases with the figures, B is a smaller upper bound on A naught than C. And then that's the contradiction. Okay, so the other direction is going to be similar in motivation. And I'll actually put those figures here. We're going to go the other way. So I've got, here's my interval AB again. Now we're going to be looking at putting the element in A naught. So we're going to put the supremum in A naught and then say, oh, that can't happen. If I have C, if I just make C A. So if I stick it all the way at the bottom, right? This would be C. Choose that. Then for the same reason we have these open set subsets going that way, we have open subsets going the other way in A naught. And there will be some E. Now, the strategy instead is we're going to point to the existence of an element, we call it Z, from the second property of a linear continuum, and say, well, now that has to exist. And this will be a contradiction. Well, I mean, there's lots of different problems here, because if C is going to be the top of A, and A has to be in that element, and essentially this B is squishing all the way down, but there needs to be room for a non-empty set over here. And then we can just shift it over. So in the same way we took this and then said, well, and it also works all the way down here. We can take this and then push it over. So even if C isn't at the bottom, and C would be greater than A in this case, or I can choose A, C, and then B. So C could just be, say, right here. Then again, we just kind of push this over, and the same exact problem occurs again. So we'll represent it formally, and this will be case 2. Now C is in the bottom, so we're not really doing this, we're doing B. Suppose C is now in the A naught part of the separation. Then again, immediately follows that this is impossible. So that leaves us with the cases we presented. Either C is A itself, or we can say C will be somewhere in the interval. Now, this should look familiar because I mean the reasoning is pretty similar, but A naught is open. In our interval, just like B naught was. Then there must be some interval of the form where we started at C and it goes up to E, which is a subset of the bottom part of the separation. But because of the order property, from the linear continuum of the linear continuum L, and that's why the linear continuum it requires both properties. So if you don't have both properties of the linear continuum, then that really convenient part doesn't happen. And we can choose a point and we call that Z. So you might be wondering, why on earth are we allowed to just put a point in here? Well, we're essentially citing the definition of the very thing that the theorem's about. And that happens a lot of times when you do theorems directly following definitions. At point Z, that's in L, such that, so if this is such that, there's lots of such that, there's such that, there's such that, there's such that. Yeah. Okay. So C is less than this guaranteed point between C and E. And then that means Z has to be. So this has to be in here, which is contrary to the fact that C is supposed to be the upper bound. C is the or wait, not the, because there are multiple symbols B and upper bound. Or A naught. So does that make sense? Basically, C is supposed to be acting as C is supposed to be acting as the upper bound for A naught. That's part of the separation. But because this interval has to exist, and because of the linear continuum property, there has to be definitionally some other point that is going to be bigger than this. So this is not an upper bound. So either way, defining that kind of middle point C, and then we show two contradictions, whether it's coming on from the top or going up from the bottom. Okay. Now, that was a lot of work. All to say that real numbers and the real line, it's connected. So you can't separate the real line, and you can't separate intervals on the real line.
This reminds me similar to the issue that we had in the fixed class integer theorem, where we tried to
Tag it,
yeah,
and then we were trying to do, well, that's covers too, because then we were trying to take half opens all the way down, and it wasn't working. Yeah. Now I'm thinking to expand that, the idea is, okay, so we took essentially a linear continuum. That's essentially what we need to work with. So if I take a linear continuum, then I need to essentially find a way to define a choice that is going to then, which I'm realizing now is actually a cover. And I was trying to go backwards, because I was saying, well, octaves cover it. But I don't think it needs to go that direction. I think I need covers to inform how I choose, because then I'm not required to have an octave. Whereas if you just choose a random thing, then it's a weak definition to then try to go back and say, well, and property of being a cover, when you could just call it a cover. So what I probably do is I'll need to find very specific properties for covers to guarantee they probably have to be a cover with disjoint subsets that have to be that are required to be close. Because if they're open, then you're missing all of your endpoints if they're disjoint. And then you'd have separation. That's a problem. Yeah, so anyway, there's a lot of cool things you can do.
Isn't that funny though?
Yeah. Because actually, now I think about it, you could probably, that's not a bad idea. I could probably start with disjoint. Well, disjoint doesn't work anymore. Because if they're closed, then they're always going to have that point intersections. So you could probably define a cover of closed sets where so if you choose two elements of the cover, then their intersection is either empty or one element, single point.
If we're saying that C is the upper bound of A naught,
Yes.
how can we pick an E that's greater than our upper bound, but still an A naught?
Good question. That open set is guaranteed by the definition of what it means to be open at something. So because A naught is open, that has to exist. So that's the whole crux of the contradiction, because we're saying we need, like, definitionally, this has to be here, but at the same time, it's contradicting the fact that we told ourselves and defined this to be the upper. So it's impossible for those to be simultaneously true. To have this be open and also this be the least upper bound for A naught. Boom, contradiction, C can't be in either side. So that means it's not even in the interval, but that in itself is a contradiction because it's supposed to be a separation. So it's not actually separated, which means it has to logically be connected. So you can never it's hard to directly prove something that's been defined as a not this. So if you make a definition A, and then you say definition B is requiring the condition not A, then all situations when you have to prove something is B, you have to assume A, and then show that logical contradiction.
I'm just thinking because trying to understand this less intuitively in my head. Tell me if I'm thinking this wrong. Linear continuum is basically any set that says if you have these two numbers, okay, then there's going to be a number in the middle. At some point.
Okay. Well, okay, so this is where it gets kind of crazy because there's lots of different ways you could approach that. In analysis, we call that density, essentially, because, well, actually, no, we wouldn't even call that density. We would call that it's a property of R that we prove that no matter what. So if like I just choose X, Y in R, like part of what it means to be R is that that's going to guarantee the existence of some Z in between. And so the idea is, how far abstract are you trying to go? Is for most people, this is way enough abstract. Topology is trying to abstract stuff that's in analysis, which is abstracted calculus. So you're trying to abstract abstractions. And that's why we have absolute ooga booga, because the issue is this is technically just example. So this is only on reals. You don't need real numbers. So if you can define any continuum, so long as it's simply ordered and so long as it has those properties, all this stuff actually works.
So the idea is to throw the real line away.
The idea is to use the real line to understand the stuff that isn't real, then you can throw the real line away. So it's like you use it and then toss. Yeah, it's kind of like toxic sports teams in college sport. Take a player, use them up, and then like, oh, okay, now I figured out how to run the team, you're gone. Okay, let's try to get to IVT. I don't know if I'll be able to do the entire proof, so I might just do the example for analysis. Because it takes time. It takes a lot of time. And for context, this theorem is one of around 27 that I proved last week. So it takes time. So you know this proof is short enough. Let's see what time it is. Oh yeah, yes. Okay. Here's how we're gonna do this. I'm going to I'm gonna do the proof. And it's gonna be confusing, and then just let me get to the example part, because then you'll be like, oh, okay, I can attach that to you.
Then why don't you do the example first?
No, but then the conditions of the example wouldn't make any sense, because yeah, it requires pieces of, yeah. So I'll just, you've probably heard of this if you passed Calc 1. Intermediate value theorem. I like to call this the duh theorem. Basically, if there's stuff, if you take something that's guaranteed, if you say it's continuous and you go from here to here, it's gonna take on every single point in between. Duh, yeah, okay, so we can generalize that to not just be true for real valued functions, any function that satisfies the necessary conditions.
David.
So what we're gonna do is we're gonna let f take x to y. Generally speaking, this doesn't have to be real numbers. We need it to be continuous though, so it'd be a continuous map where the space X is required to be connected. And the nice thing is we just spent all of that last half an hour proving that the real numbers are connected. So we will be able to immediately use that. Connected space. And Y is an ordered set. Yeah, that's right. We get it to be ordered. In the order topology. Now, here's the part that should look familiar. If we take 2 points in the domain space, and then we also choose some point in the range space, such that f of A is less than R is less than f of B, or could be the other way. We just need it to be between, so it could be f of A is greater than R greater than B. Either way, we're saying R is between A, f of A, f of B. Then there has to exist some C in the domain space that's basically assigned so you can map C to R. So if I'm choosing something between in somewhere in the image, then it needs to have a source, given the above condition. Okay. And Dr. Lang, I'll put out the whole analysis example after. So assume, I love this. I'm gonna start adopting this because Munkres gave me an out. He just said assume the hypothesis. So you don't have to write it all over again. Assume the hypothesis. I don't know why I never did that before. You didn't really think that would that's nice. Okay.
Assume give up.
Because that way you don't have to rewrite the entire thing. So then the sets. So the crux of this one is a little trick. So we're gonna take A to be, here's a little notational thing. So I personally, some textbooks will use smooth parentheses here, but whenever I'm doing a set, I like to indicate that this is image. So I use a hard bracket. So this is basically not just f of some point x. This is the image if I take all points in this space and that set of what's going to come out. So it's the image. So I take this image and I'm going to intersect it with this ray. Kind of similar to what we're talking about, but now instead of it being horizontal, we're looking at the vertical ray. And we're going to define B very similarly. So we'll take the image intersecting it. Instead of the bottom side, we'll do the top side, right? Okay. And then these are disjoint by the way we chose to define them, because there's R's missing in between.
That's not before you continue. There's just one thing that I just don't understand. Is that if the idea is that we're trying to go beyond the real numbers, except we're still using smaller than or bigger than, which I thought kind of lost their meaning. We left the real numbers.
That's a good question. Last semester, and also if you take, are you in higher algebra?
Probably.
Okay. I might, you know, I'll probably I might scan some of the set theory and put it in there. But because this relation is actually generalized to just an order relation. And so order relate, you know how equivalence relation needs to satisfy that saying, so like for equivalence. You need, so for the classic example, it's equals, but for abstraction's sake, I'll use it tilde. So we need to have x relating to x for all x and x. Now, if x relates to y and we're equivalent, then y better relate to x. That better be true, not just for some cases, that better be true for all cases. And then if x relates to y and y relates to some z, again, where relation is equivalence, we would hope and we require that then x relates to z the same way, so it would be equivalent. That needs to be true for all triples. So this is equivalence. Now, equivalence is not the only kind of relation that's happening. So relation could be something like the order relation. So order or simple order. Now that's typically how we indicate it, but it'll have different properties. So we'll have things like x is never happens. Now it's worded differently when you do it in set theory, but that's essentially the crux of the matter. You're
Right.
guaranteeing that that can't be a thing. And that you got this transitivity still comes with it. So x less than y and y less than. The thing is, we still use the words less than, even though it might not necessarily be at all.
Okay.
Is still going to give x less than z. And there is a third property. I'm just blanking on it right now. But the idea is you can abstract this concept of order to then define these things called ordered sets, where you impose this relation onto a set and say all elements have to obey. In the same way that we can do that with equivalence relations to do partition.
I see.
Mhm.
But so like, say the complex numbers, they would not obey those conditions. Probably. Do they?
Well, you could, so that's the thing, you could define different kinds of ordered relations. So you could define an order relation that would do like a dictionary order. And then that would work in C. Whereas, so not all relations are going to work for all sets. You kind of define the relation and pose it on a set in a way that makes it work.
I see.
So that's why it's important that Y is an ordered set. That means
Yeah.
it's not necessarily a set of numbers, but it's a set of objects that we can order in some way.
To guarantee that we can always take all of the elements and essentially line them up if we had to in the order that they come. So I'm counting is what everyone starts with. So that's the most obviously ordered thing, but you can technically define other order, other kinds of orders to. Think about a dictionary. I mean, that's obviously not in this linear string, but there is some rhyme or reason to it, right? You look at the first character, and then the first characters are ordered under some rule. But then you have the rule that essentially, if they're equivalent, you go to the next character and you do the same thing over and over again. So that would count as a dictionary order. And that's where we get the name from.
So just by the name, right, it must be true that there are some sets you can't order,
Right.
which is actually more surprising.
Then not, yeah, actually. Because you would think, oh, why don't I just say this one is, you'd have to finite point, every single one.
You're close with the complex number.
Yes.
Complex numbers with traditional sets of distances, we can't order those, but there are other orders that you can put. But there are some sets you cannot order.
A and B are not empty, given the way this continuous mapping in the image and intersection. Because one contains f of A and the other contains f of B. So the reason why we have to say one contains one the other, because it's either case. So that's the only reason why I can't just say f of A is specifically in A or B.
Interesting that they let that flow abstractly rather than assuming without.
Yeah, especially because the thing is, it's still technically it's general,
Right.
but A and B are open in the image. Because they are a finite intersection, so being the intersection of an open open ray in Y with the image, which is open. And if there does not exist, we're going to contradict. There is not some point in the domain space that you can map to the R that is between. Then the image constitutes a separation. A, B constitute a separation of the image. Now, where is this immediately a problem? Well, this is contradicting the fact that the image of a connected space, which in this case is X by hypothesis.
Wait, Scott?
Yeah.
Real quick, I'm still reading back what you're saying. So it has A, B open in the image being the intersection of an upper ray.
Oh, sorry, open.
Oh, open.
So these are open rays, minus infinity to R, R to
Oh,
infinity.
okay, open
Yeah.
because,
So we're intersecting image with a ray.
okay,
Yep, and since they're both open, then finite intersections of open sets are open.
okay,
That's a definitional type, yeah.
Okay.
Okay, image of connected space under a continuous map. I don't know how to do ends anymore. Okay, map is connected. Now, is the last statement obviously not trivial? Yes, had to prove that in the previous section, but not enough time right now. So that's why we require the domain to be continuous. Because technically, if you don't have a continuous domain, its image is not guaranteed. And because of that, then there wouldn't actually be a contradiction. There could be a point when you could just, have it not inside. Okay, so the picture is the classic. We're evolving backwards, not playing to count one. But it is really pretty, almost as beautiful as the epsilon delta generalization. Is because in calculus, we say, okay, so I'm dealing with X is a closed interval. Ever wonder why all the textbooks say AB is closed? AB is closed, well, it needs to be closed in R. And then obviously our range space is simply the reals. So that when we have our mapping, we're taking some sort of a closed interval into a real, so a real value function. So this is connected in R. Why can I say that's connected in R? Because it is an interval subspace of a connected. And we just proved earlier that that is connected. And then obviously,
but why do you need to say in R? Can't you just say it's connected?
I could. It's just basically to be clear, because now, again, since we're not technically assuming that everything is in R, it's nice to be able to say, yeah, this one actually is in R.
Oh, okay,
We're grounding ourselves. R is ordered set in the order of G. So the conditions are met here. Now I'm just going to choose A, B in this interval, and then choose an R between F of A. Okay, so here's the business. Here is R, and here is R. And if I can choose some closed interval A to B, and then this is right here, F of A, and have it end somewhere. This would be F of B. So now this is the image set. And then we can have some sort of a function, continuous function, doesn't really matter. And now we choose an R between, so if I choose like this R. Now I need to define the rays accordingly, so the rays are going to be from R to minus infinity, but it intersects with here, so then it intersects at the bottom. And then it'll intersect up here. We have these two rays. And so those are the, and then this comes across. And we're guaranteeing the existence. And I like this example because usually they only show one, but this really that it could be more than one. C1, C2, C3, which is equal to R. So here this would drop down to C1, C2, C3. Now, obviously, this doesn't have to happen, but it's accommodated by the theorem. So here's what we're looking at. Our A from the proof in this case is the image of X intersecting this ray, which, if we apply it to this scenario, is the image of A, the integral A to B intersecting minus infinity to R, which is the integral f of A, f of A to f of B intersecting to R. That's
Just say that of A12.
which is, yeah. F beta. And then B would be constructed the same. And then here's kind of, you can see it by contradiction. So if R was not in AB, or the image, sorry, not the integral. So the image would be f of A, f of B. Then that means AB actually becomes separation.
But I thought that they couldn't have empty sets, and one of those would be empty, right?
Well, so here's the thing. Basically, visually speaking, imagine you do have just these open sets. And then you're trying, so the goal is, let's try to separate this.
Try to avoid R.
Yeah, let's try to avoid R and somehow just get all of our domain avoiding R.
Mhm.
Well, this is continuous map, which means that this right here, from here to here, that image is connected.
Right.
So if we don't include R, we're essentially splitting. We would have some sort of an A naught situation, B naught situation, where we've got non-empty sets that are suddenly disjoint because they're missing R. And that by definition means it's separated, which is exactly the opposite of being connected. And so the reason why we're required to have the relationship between the points with every single thing is essentially, the bottom line is to satisfy the definition of connectedness. Yeah.
Okay.
So that's the real reason why you can't pick your pencil up off the paper. So a little overtime,
Oh,
sorry
that's
about that.
good.
It's a lot of fun. It's pretty crazy.